Okay, I think we will get started with the webinar now. So first of all, I want to thank each and every one of you who have joined us in this webinar today, and thank you for taking your precious time out and joining us in this webinar. So as you are aware, so today's webinar topic is on generative design for lightweight engineering. I will get started with the webinar. So give a small brief introduction about LaunchTech Solutions. We are an engineering company. We are a small, team of budding engineers based in Abu Dhabi, UAE, and we specialize in mechanical design, simulations, and advanced FEA modeling. We also have a very strong partnership with our software developer, that is Dassault Systems, and we are the official software distributor in the Middle East region for Dassault Systems. We also do the development and services for Dassault Systems in the Middle East region. On top of that, we are also a certified education partner and a certification center. We also provide trainings on all the Dassault Systems software suite. So what are the services offered by us from LaunchTech Solutions? So one thing, as I said earlier, we distribute the system software in the Middle East, ranging from different brands, that is from CATIA, BioVia, Simulia, Innovia, and Delmia. So each of these terms means CATIA for design, BioVia for material design, and Simulia for simulation-related activities, and Innovia for project management, and Delmia for digital manufacturing. And we also give consultancy services for the technical projects, and we do conduct software technical trainings based on the softwares used in the manufacturing industries, and also we do provide certifications for all these softwares, which are highly which are a standard in the industry and are highly recognized worldwide. Coming to the topic, what is generative design? What is the webinar all about? So today we will see how design was done earlier in a very conventional way or in a traditional way, and what is the standard in the industry, what is the current industry requirements, and what is done in the present market. So earlier, during the traditional design, the designer, they used to design a component or a product based on the established practices, whatever the best practices they were there, or they were designing the components based on their past experiences and the history, and then they used to make use of the existing design iterations which was there earlier and design their product on top of it. Now with this approach gone, now it's all about the generative design. So now optimal design, whatever we design, is totally computer generated, and it is completely requirements driven and results based on the function of the part. So instead of asking the question earlier, does this shape meet the requirements, now we are asking and exploring the options like which shape will best meet my requirement. We will see a bit more in detail in the next slide about what I'm talking now. So as you see on the left side, that is a bracket which we are taking as an example today. We will take this bracket as the example and see how generative design will help us in generating a topologically optimized shape for it. So from the traditional approach, which was a generalized CAD, which is the computer-aided design, now we are moving towards the cognitive augmented design. So when I make use of the word cognitive augmented design, what exactly it is? When I say cognitive augmented design, earlier we were giving instructions to the computer. We were seeing the screen, we were designing the 2D, 3D, and the entire product, right, based on the requirements. Now we reduce the workload on us. We say, okay, these are the inputs which are which are the KPIs, or which will affect my KPIs. So based on these inputs, now we expect the computer to design and give us a shape, and the computer, leveraging its computational power, will do all the possible iterations which the human has to do. It will do on its own and then give us the result. So this is called cognitive augmented design. Okay, with this, what we can achieve is we can explore unimaginable shapes while respecting the design specifications. Okay, so this in turn will help us meet our KPIs and the desired stiffness and the strength of the part, the desired time which we require to design the entire product. It will result in cost saving, and also it will give us the uh, option of using different materials to do our prototype, and then at the end, with respecting the mass or the product which we are using, it will help us to keep that mass of the product into consideration and give us the end product. So we're talking about the generative design. So there should be one solution which should be enabling this. So that is 3D experience platform. So this platform is used for all the activities. Like we start with the project, and then we get into the concept design, then we get into the engineering design. From the engineering design, we get into the simulation, and then once it is validated, we get into manufacturing. So all these processes are handled within a single platform, and that is 3D experience platform. Okay, so with this 3D experience platform, we kind of get the digital continuity. So when I say digital continuity, if you see the image on the left side, we see our engineering design, and then we see the simulation, right? So, and in between we also see a wall. What that means, and on the left side we see there is just one 3D experience platform, and then we see the design and simulation together. So what it means and what is it, I will talk a bit in detail in the next upcoming slide. So with the traditional approach, taking my previous slide into consideration, if I see on the left side, I see two designers. Basically, one is the CAD designer and another person is the simulation analyst. So these are the people that are in any of the engineering teams in any of the industries, right? So earlier, what used to happen is we had different softwares doing all the jobs. Like for the design, we had one software. For the simulation related needs, we had one more software. And it's a very long iterative process. What used to happen is the CAD designer would start with his design. Then once he is finished with his design, he will send it to the simulation analyst, where the simulation analyst will do the meshing, simulation setup, then perform the topology optimization. From there, again, he will send that model to the CAD designer. CAD designer will do some changes based on the simulation analyst's input, and again, he will send it for the model validation. And again, it is sent back to the CAD designer for the model reconstruction. So when doing this activity, the data interchange happening between the CAD designer and the simulation analyst, there is a huge silo in between. Like CAD designer has to design, export, and give it to the simulation analyst. He will open the product in a different software. The data related problems will come, and it mostly results in it's a very time consuming process, because it's continuous to and fro activities to kind of get the to get the end product. Whereas if you see on the right hand side, with the 3D experience platform, what happens is you start with the design space creation, you do the meshing and simulation setup, you do the topology optimization and validation, you do the model reconstruction, and then again you do the model validation. And for the second iteration, you can start with the first step. So all these operations or the processes can be done in a very single place, not leaving the software at all. Okay, and here everybody will be referring to the same data, and there is continuous digital continuity, resulting very less time consumption for the entire topology optimization process, and to get the final product. So we have a small question just to keep the session a bit interactive between us and the attendees. So there's a small question coming up for you to answer. Getting to the next part. So what are the stages that are involved in the functional driven generative design workflow? What is the workflow which we are going to follow? First, we start with the functional specification. When I say functional specification, it's the CAD part which we are going to work with initially. Okay, so first we start with creating the design space and mechanical interfaces. as the next step, then we define the load cases and we define the boundary conditions. From that next, we will go and define the target and constraints, that what is the maximum stiffness that we need, what is the mass that needs to be reduced on the component, what are the manufacturing constraints that I'm going to apply, what is the thickness, and does the part which is going to be optimized, does it has to follow a particular symmetry. These parameters are given. Once that is done, next what we do is a system will generate a design, a topology, based on the inputs given, and from there we will see, we will get to see, we will explore the concept by changing some parameters. Then once we are happy with the concept, we then do the concept generation, where the automatic solid modeling will happen. And once it is done, again we will do the concept structural validation. And once we are happy with the structural results, then we get into the alternative creation. That means then we see using which method we should go for the manufacturing. Okay, and that is the next detailed design. We call it as detailed design. Okay, so here, as you see on the screen, there are two methods which we are going to see. One is the additive manufacturing and one is the milling. So with respect to two of these manufacturing techniques, we can generate our topology. Okay, so we do the detailed refinement, then we do the structural validation, and finally we do the design review, and then it goes for the manufacturing process and simulation. So as you see this, as this arrow indicates, the first and second processes in the workflow are an iterative process. Either you can start with the functional specification, you do the concept trade-off studies. If you are not happy with the trade-off results, then again, you do one more iteration, you do some changes in your design space. Maybe you will, increase that design space a bit more, so that it can have enough material to withstand all the stresses, which is with the stressors, loads, etc. And once you are happy with the concept trade-off, you can directly get into the detailed design part of it. Now, this is a small video. These are some next videos where we will see that how the entire process is done inside the 3D experience platform, avoiding all the silos. So as you see, now we are starting with the design space. So this is the space, or this is the entire material block which we will feed to the system, and then we define all our load cases to get a concept shape, which is topology optimized. So first we do the partition of the design space. And one more important parameter that we need to notice here is on the right hand side, we see a menu over here. So this is called design assistant or the exploration assistant. What this does is it will tell us each and every single step that we need to follow to get the topology optimization or to generate the concept shape which we are looking for. As you see, if we go and refer to any other softwares in the market outside, the designer or the simulation analyst is expected to know a certain process. Okay, because the CAD engineer might feel like, okay, simulation is not my cup of tea, it is a difficult process. And it's a vice versa. The simulation person can say like, okay, I am not good with CAD, I'm only good with meshing, I can only do simulations, I do not understand CAD. So to avoid this, what they have done is they have created this menu. It's called as exploration assistant, where they have defined the entire step to step which needs to be followed in a very intuitive manner. So any person with a very basic knowledge of the mechanical design or simulation portfolio can run this and have his concept shape generated. So as you see, there are different steps included here. One is the design space setup, where you define the design space and the functional regions of this component, and then you do the meshing setup, and then there is analysis setup, and then there is setup validation. You define the targets, what is the mass that you want to retain, you define the constraints, then you control your shape. Maybe you want it symmetrical or something, you control the shape, and then finally you do generate the concept based on these inputs, and finally do the design validation. So we will see one by one how these processes are done. So now he's defining the functional regions. So as you see over here, there are cylinder kind of things. So those are the places for the bolts to hold the design, right? So they are defining it. So as you can see here, he's doing all the, he's giving all his inputs. So now he's doing the meshing setup. He's designing what kind of mesh that he needs. What is the type of mesh that he wants to, do? What is the order? Is it the linear, or what is that type? Is it tetrahedron? He'll be able to define all that here. So once the meshing is done for the analysis case, yes. So in this analysis setup, we can see that there are loads, restraints, thermal conditions, load cases, connections are available. So we can define one by one what and all is applicable over here. So first we define the loads. So what are the remote forces acting in XYZ direction? What is the force that is there on these points? So we define all that, and we define our load cases. And there is something called load case manager. So once you have defined all your loads, you will kind of get a menu with all the forces that are acting on this particular component, and you will be able to change the parameters from here. You do not need to go to the design again to do any changes. With this load case manager, you will be able to change the values which you had given over here, and based on this you can select what are the load cases that should be applied at a given point of time to generate your concept shape. We can do that. Once that is done, we define the connections. So you can also state like, okay, we are going to fit a bolt here. You can give all the parameters of this bolt. And you can just automate, you can just let the system choose what are the other positions where you want to fit the bolt. The system will auto calculate its position and place these bolts. So once you are done with it, you kind of do the shape controlling with the symmetry, etc., and then you get into generating your concept shape. So you submit your job. Once the job is submitted, you will get to see the results, and also it will say that it will tell you, once you say that the compute shape, it will tell you the shape is computed, that the execution is complete, and all constraints are met. And you will get to see the summary and the results and the history over here, like what is the time taken for the entire job duration, when did the job start, what is the end time, if the design was able to meet, or the computation was able to meet certain constraint, or did it fail anything. So all these details will be available for you. And in the history, you will be able to see the stiffness measurement graph as well. And once you are done with it, then you can get into generate your concept shape. So this is the concept shape which is available for you at the end of your computation. So once it is done, what we do is we get into the trade-off study. So now we have our computational shapes, right? So now it is essential for us to do a trade-off study. With the trade-off study, what I mean is now, you might have generated, now you want to, there are two manufacturing processes, which actually three manufacturing processes which we can follow. One is the additive manufacturing, and again, there is one more is for milling and one more is for casting. So with this trade-off, what we mean to study is, with the whatever the computed shape, we have a legacy product. With the legacy product, what is the mass of the product, or what is the mesh size it is having, what is the maximum stiffness the component is having, all that details will be available over here. With that, we will be able to also see what are the different governing KPIs. Is it able to meet our requirements? Like, what is the one mass stress we wanted in this component? And all that details will be available for us to visualize in the trade-off study. With this, we will be able to decide, okay, this is the best design, which I want to take, and I want to use the additive manufacturing method to generate my component. So that's what we do with the trade-off studies. Yeah. So once it is done, we get it to the geometry reconstruction. So now our the 3D geometry is ready with the new topologically optimized shape. Now what we do is we kind of do a little more engineering design on it, and we make it look a bit more nicer. So with the we kind of use this imagine and shape methodology, where we kind of draw these tubular structures over here, and we initially define a skeleton of it, and then using the advanced join options, what will happen is all you have to do is just select each of these previously drawn cubes, and your geometry will be automatically created. All the joints will be automatically performed, as shown over here. So once it is done, and because we know that our computed shape will be symmetrical in nature, we just take half of the part and just do this reconstruction, and then the other can be automatically mirrored. Now what we did is we recreated the entire geometry. Once the geometry is recreated, we can do furthermore optimizations on this. Now we can validate the updated concept shape, we can do the structural validation on it, and then also what we can do is we can also parametrically optimize the concept shape. What we can do is here, okay, we have certain radiuses or the circle definitions. We can say, okay, this is the shape which I'm not happy with, maybe the stresses are more at this particular given region, and my material is this particular region will not hold that much load. So what can I do? So now either as a human we can do some calculations, do a to and fro activity, and uh, change that particular zone, how it looks, etc. Other than that, we can leverage the parametric capabilities of the platform, where we link each of these parameters with the stress results. Okay, we define the parameters, and then we link it with the constraints. Basically, we select the constraints, like in particular here we say with the Monmeister stresses, we say, okay, this is the constraint that you need to obey. We kind of define the rules. Once the rules are set, and then once we do the we run the analysis or the simulation, it will respect all these parameters and give you a optimum shape. Okay, so once it is done, it will automatically update the geometry and give you all the results. Okay, and it will tell you, okay, all the constraints are met, and this is the shape with respecting to the provided constraints the system is able to generate. And once it is done, we can again finally do the validation of it. Second is we will see how we can once the optimum shape is generated, how we will see how we can manufacture with respect to the milling. So automatically we can calculate the block or the material for what the milling will be done, and then for the milling reconstruction we can define all the side profiles of it, how the block should look like. And once it is done, as you can see, we have already defined the partitions, and now we are ready to generate the concept shapes. Okay, now we are defining the directions as well with respect to the tool diameter, which tool will be used to do the milling operations. So with this is the basic shape which is being developed. So you can optionally modify these generated sketches as well. So once this is done, you can further define your concept. You can define which are the places that you want to constraint. Again, this, I mean, in this particular design, where you are going to kind of put the bolts, where you are going to fix it on the machine, all those details you can give it. Okay. So once that is done, yeah. So once the refinement is done, finally you do the validation to see the updated concept shape, whether if it is meeting all your KPIs or not. So yes, so now you can do the cross comparison. So now you see with the legacy product, we have the mass of around 414 grams of the the end product with a buy to fly ratio as 8:1. So before I say buy to fly ratio, I just want to explain what actually buy to fly ratio is. So it is nothing but the ratio of the mass of the starting stock of material to the mass of the final finished part, right? So that is the buy to fly ratio. While doing the comparison, now we have two options. We have generated one for milling and another one for additive manufacturing. With the milling, you can see as the weight is 324 grams, it's 78%, where the buy to fly ratio is 14:1. And also at the same case with the additive manufacturing, you can see it as with the same load cases, with the same stresses, everything in the material, with this particularly optimized shape, it is just 231 grams at the end, which is just 55%, and the buy to fly ratio is 1.3:1. That means at the end of the day, we can determine that, okay, going with the additive manufacturing process will be more beneficial, in terms of cost saving, in terms of time, and in all other aspects, with respecting to all the inputs that you have given, and considering all the load cases and how the material will behave or the product will behave under different load cases. So yes, so this is about the process, and now we just saw the entire workflow of how the generative design is done instead of a traditional design within the 3D experience platform. And yes, so this is it. Now we will answer a small poll and we will get into the next slides. Okay. Thank you, everyone. So yes, so far whatever we saw on the platform, there are two roles which we used in the 3D experience platform to kind of do all the processes. So here, what we saw to do the entire workflow. One thing is the function-driven generative designer role, and another one is the function-driven refinement design. So when I say role, in the 3D experience platform, there are roles which will allow like a mechanical designer role or a simulation analyst role. So these are structured and created with different end users in mind. Let's say if I talk about mechanical designer role, the mechanical designer role will be only able to model the initial design, and that's it. His roles and responsibilities that much, and he will get only those many tools inside the platform to create his design. And if I say simulation analyst, and in that particular role, you will get different simulation capabilities, simulation tools a simulation engineer would require to do all the FEA simulations. Okay, so it is structured in that way. So that is called roles. It will give you access to a set of predefined tools which will be used in the day-to-day engineering processes. Coming to the functional driven generative designer role, it is also a role. It is a hybrid role. We can say it gives you capabilities of both designing the component as well as doing the simulations inside the component. Okay, so here with this particular role, you will be able to explore and generate the organic shapes, and you will with the dedicated manufacturing process. We will keep that end manufacturing process in the mind, keeping that, okay, we want to use milling or we want to use additive manufacturing. Respecting this, we will define all our inputs and then generate the final computed shape. With this, you will get a very intuitive workflow assistant guides. As I told you in the beginning, you will get a set of operations that you need to do. The system will tell you, okay, these are the next steps that you need to run in order to get this. You will be and then extensive optimization setup capabilities for frequency displacement, stress and manufacturing constraints. You will be able to easily validate the structural behavior of concepts. You can reuse the entire analysis you have done for validating the design at all stages of the processes. And again, you can create different variants to explore. and for the compare and assess different configurations that are possible against the KPIs defined, and then finally select the best concept. And similarly, with the function-driven refinement designer, whatever the the component that you have generated topologically, with the optimization, you will be able to recreate the CAD structure of it. Basically, you refine the entire design, because the when we say organic design, it might look a little out of the box. To give it a proper shape, to make it look much more aesthetically nice, we can leverage this function-driven refinement designer role, and then do all the design changes. So this is again accessible directly within the function-driven generative design workflow, and it drives the design to meet the KPIs by leveraging single objective parametric optimization, and it also reduces the local stresses and further reduce mass through the shape optimization processes. So this is about the two roles which we have, two roles which we have used to optimize the product and have seen in the previous videos. This is a small customer case study. So everyone knows Airbus. So we all know that basically the design or the FEA or CAD are not the new technologies. So why did Airbus, wanted this? So basically, the function-driven generative design tool was developed by Dassault Systems specifically on the request of Airbus, because they kind of asked to bring FEA, topology optimization, and design into a single application, because there, as I mentioned earlier, there were many silo-based applications earlier where you have to do this to and fro approaches. With this request, Dassault Systems developed this entire role, and this kind of helped Airbus to gain a lot of productivity. So here are some metrics and comments which are directly coming from the customer. These are not by LaunchTech or not by Dassault Systems. This is said by the customer. So the most significant metrics which we can notice here is 150 full-time users using the solution in the production, with almost significant growth in users. I mean, okay. So, and then a buy-to-fly ratio was considerably reduced by up to 10 times. And the weight reduction they achieved was nearly 30 times with respect to the traditional manufacturing approaches they were following earlier. And that entire design development time was significantly reduced by almost 60%. So this was the comments which was given by the Airbus technical authority. So as we saw, the highlights of the solution are it provides you a very intuitive workflow, assistant guides which help you and guide you in the each step to do and tell you what is that you need to do next. It will import and de-feature data from any CAD system. You can even import a CAD which was generated in some other software, get into inside the 3D experience platform in the step or IGS format, and then do the de-featuring of it. And then you can apply your loads, boundary conditions, and define your connections. You can do your extensive optimization setup capabilities for frequency, displacement, stress, and you can define the manufacturing constraints. Then you'll be able to easily validate the structural behavior of the concepts, and you'll be able to create variants to explore, compare, and assess different configurations against the different KPIs and select the best concept, leveraging and by doing the trade-off studies. And you will be able, not only that, at the end you will be able to reuse the analysis to validate the design at all stages of the process. And this will be saved. This all will be saved inside the platform. And at any given point, if you want to do some minor change, even after a year after you're done studies, all you have to just go and tweak some parameters, and your model will be up, ready in front of your eyes in a very less considerable time. So the main takeaway from today's session is LaunchTech solutions with our partnership with Dassault Systems. We deliver very unified solutions for the design, simulation, and manufacturing. supporting additive manufacturing and other conventional manufacturing processes. And we leverage a 3D experience platform and other our legacy products intended for each of these processes. With the 3D experience platform, we provide the designers and the simulation engineers, the manufacturing engineers, they will be able to work on a single collaborative platform and leverage the platform and refer to a single data as a single source of truth. And then you can embark modeling, simulation, and optimization in a unique designer role. That means whatever we saw, the function-driven generative role is an example of such capabilities. All the functions embedded into a single role, making it a very powerful solution and powerful role. And then we also deliver a unique generative manufacturing process and simulation solutions. Okay, so you can note down the mail address, and you can also visit our websites. And there are some couple of useful blogs on the different solutions which are offered by us, which take care of certain problems the industries are facing currently. And thank you so much for attending this small webinar. We hope to see you soon in our next webinars. With this, we end our webinar. Thank you so much.